Can you hear me? I'm talking now. Okay, good. Josie Ann, you're good? Okay. All right, well, I'm going to get started because we have a bunch of problems to go over. So we're starting in we're in 13 now, chapter 13. Nobody sent me questions, so we'll go ahead and use the ones that I had posted. So 13.1 is sampling, and your book went over 5 different types of sampling. Random sampling, where every item or every sample is equally likely to be selected. And then we had a systematic, which means we take every nth item on a list, or especially this is used in production lines for quality control testing, because it's real easy to pick a random starting point and then take every 10th item that comes off the production line or something like that. Cluster, sometimes called a geographic sample, and a cluster sample, the randomness comes here when we select the clusters and then we sample everything in the cluster. And stratified, the population is already divided into groups that are have a common characteristic, maybe gender, race, religion, income, and then we take a random sample from within each of the strata. So contrast that to cluster. Cluster, we don't use all the clusters. Stratified sampling, we take a sample from every grouping, every stratum in the population. And then convenience is data that are just easy to get. And this is generally not representative. It's not a good sample to use to make a statistical inference. Okay, what about a census? Census is where we count everybody. And in the United States, we do a census every 10 years. And the last one was done in 2010. And sometimes we do what's called an attempted census, when we try to contact everybody, but we don't get data from everybody. Right now in this class, we're doing the student survey of instruction, and that's actually done as an attempted census because we try to get all students to answer. But a lot of times we don't get responses from everybody. That would be called an attempted census. But a true census is where we measure every person in the population. My throat, and I keep coughing. So, okay, so let's go through some situations and identify the sampling. So the health department randomly selects 5 stores from each of 4 randomly selected sections of the city and checks food items for freshness. The stores are used as a representative sample of the entire city. What kind of sampling are we doing here? Yeah, this is cluster. Very good, because notice where we're randomly selecting the stores. That makes it a cluster sample. And then how about every 14th person in line at a grocery store is asked about their satisfaction with a variety of products. This is a pretty easy one. Remember, we did that. 14th makes it, what kind of sample is that one going to be? Yeah, that's a systematic. Yep. The Student Senate at a university is electing a new president. The first 25 people leaving the library are asked for whom they will vote. What kind of a sample is that going to be? The first 25. Is it really random? They're taking the first 25 coming out of the library. Yeah, this is a convenience. Remember, think about it. This is easy to get. So rather than saying we take every 10th person leaving the library, which would be systematic, they're just taking the first 25. So that's a convenient sample. Businesses in Iowa City are grouped according to type: medical, service, retail, manufacturing, etc. A random sample of 10 is selected from each of the business types. What kind of sample here? Now notice again, the population is divided into homogeneous groups, and then in each of those groups we take a random sample. Anybody want to try that one? That one's called... No, not systematic. No. Yeah, this is stratified. Yeah, sorry, this is stratified. Yes. Okay, they're divided into business types, and then we take a random sample from every one of the types. Different from cluster, where the clusters are groups that are there already, but then we only take a random sample of the groups. Here we're going to use all the business types. So that's called stratified sampling. A nonprofit group sponsors a raffle to earn money to fund its programs. 500 tickets are sold at $5 each, and the winner receives a check for $250. This almost sounds like our expected value from the last chapter. The nonprofit CEO randomly selects one ticket from a bin and announces the winner. What kind of a sample is he taking here? It's actually only pulling one ticket out, but what would this one be called? This one's a true random sample. Yeah, everybody's equally likely to win. Okay. All right, let's try another scenario. So it's the same situation here. We want to get a sample of passengers on a flight, and we're going to use 4 different methods, and let's identify the methods. Pick every 10th passenger as they board the plane. What kind of a sample would that be? Every 10th person. So that's going to be systematic. Yep. From the boarding list, randomly select 5 people flying first class and 25 of the other passengers. What kind of sampling do we call that one? Now, it's not convenience. They divided the passengers into 2 groups, first class and everybody else. And then they took a random sample from each of those groups. What kind of sampling is that? Not cluster. This is stratified, okay, because we divided the population into 2 groups. Each group has similar characteristics, so all the first class people in one group and then all the other passengers in the other group. Stratified sampling. This one, randomly generate 30 seat numbers and survey the passengers who sit there. What kind of sampling would we call C? Oh, I'm not at the bottom here. Yeah, C is just a simple random sample. Yeah, this is a random sample, C. Randomly generate 30 seat numbers. Everybody's equally likely to get picked here. Now look at this last one. Randomly select a seat position, right window, right center, right aisle, etc., and survey all the people sitting in those seats. Okay, Ernestine, here's your chance. What kind of sampling is this one? This is cluster, yes. This is cluster because we randomly selected one group and then we surveyed everybody in the seats. See the difference with this one? We have people in 2 groups. We don't randomly select the group. We use all the groups and we take a sample from each group. That's stratified. Okay, let's try another one. The government of a large city needs to determine whether the city's residents will support construction of a new gym. They decide to conduct a survey of a sample of the city's residents. Which one of the following procedures would be most appropriate for obtaining the sample? Survey a random sample of future employees of the gym. Survey every 5th person to enter the local church on Sunday. Survey the last 100 people listed in the telephone directory. Survey a random sample of persons living within each neighborhood. Which one? D. Yeah, D makes the most sense. Okay, these other 3 are not going to really get us a good representative sample of the people who are going to use the gymnasium. All right, challenge question. I like this question because it kind of makes you think a little bit. Some subscribers of Consumer Reports respond to an annual questionnaire about their satisfaction with new appliances, cars, etc. The information obtained is then used as a sample from which frequency of repairs and other ratings are made by the magazine. So the first question is, what kind of sampling are we doing in this situation? Or what kind of sampling is Consumer Reports doing? Anybody want to try that? What kind of sampling are they doing? Well, this is really an attempted census. Okay, because what they actually do is they contact all the subscribers and ask them to fill out this questionnaire. Are the data that are obtained from the return questionnaires representative of the entire population, or do you think they're biased? So what they'll do is they'll mail, yeah, this is biased, and I don't think a lot of people understand this when they read that book, that Consumer Reports publishes a book each year with ratings on appliances and cars and all, and it's really not a very good representative sampling of people who purchase those appliances. It's biased because the fact that who's going to most likely send us back in? People who are really very happy with the product or very unhappy. Yeah, this is a really biased sample, and I really don't think people understand that when they see that book that they published. Okay, so we don't do 13.2, And then we move to 13.3, and you don't have to know how to make the graphs here. You're just going to interpret them. So a piece of data is a single response to an experiment. So for instance, if I flipped a coin, the outcome I got, a head or a tail, would be a piece of data. And we can do a frequency distribution. We can list the observed values and the corresponding frequencies of each of those values. So let me go on the next page because I have an example. So here they did a survey and they asked, I think this was based on families, how many pets they had. So in that survey, 6 families said we have no pets. 10 families said we have 1 pet. 8 families said we have 2 pets. 4 families said we have 3 pets, and then 2 families had 4 pets. We can use this summary table, it's called a frequency distribution, to construct a histogram. And again, I'm not holding you responsible for constructing these, but being able to read them. So here's a histogram. Here's one I made, the same data, I put it in Excel. It's using this data and making a picture of it. Okay, here's another picture here. All right, and we're going to talk about histograms in just a second, but this is what the data display looks like. So you can see a lot more here than you see here. So let's use a frequency distribution now to answer some questions. What are the total number of observations in this table? How do you calculate that? Total number of observations. What do you do to find out how many total observations are in a frequency distribution? You simply add up the numbers here. So 4 and 3 is 7, 9, 10. So not 6. Be careful, Josiane, you actually add the numbers here. It's actually 19. Okay, so 4 plus 3 plus 2, etc. So 19 different people, whatever this survey was about, answered the question here or were categorized in this table. The modal class, the mode of a distribution, is the most frequent. So in this frequency distribution, we call these classes. What's the modal class here? Which of these has the most observations? 32 to 38, yes. Absolutely. Okay, let's do another one. Okay, so here's a graph of the number of soft drinks purchased at a theater. So people that went to the movie or the theater purchased 1 through 6, and the height of the bar tells me how many people purchased. So 3 people bought no drinks. 3 people bought 1 drink, 7 people bought 2 drinks, etc. That's how you read that display. How many people were surveyed? Now this is a little bit different. Let me just flip back to the prior one. On here, when I asked you how many people, all you did was add the numbers up. Now when you've got the display, whoops, to find out the number of people here, you're going to add the height of the bars. So what do I have? 3 plus 3 is 6, plus 7 is 13, plus 4 is 17, plus 3 is 20, plus 2 is 22, plus 1 is 23 total. Okay, so it's a little bit harder on this display to find out the total number. 23. Good. Okay, next question. What's the modal class? Notice on the histogram you can see really nicely which class has the highest. It's the 2, right? The most people bought 2 drinks. How many people bought 4 drinks? How many people bought 4? So you go to the 4 bar and you look at the height. How many people bought 4? It's actually 3. Yeah, Ernestine got it. Good. How many soft drinks total were purchased? Now this is a little trickier. How many total soft drinks were purchased? Okay, now it's not 21. Now be careful. So let's look over here. So in this group here, 3 people didn't buy any drinks, so no drinks here. How about here? 3 people bought 1 drink. So I actually could start putting the numbers on here. So this is a 3. So in this group here, there was a total of 3 drinks bought. How about in this group? These people bought 2 drinks, and how many people were in that group? 7 times 2 is 14, right? So 14. All right, and then the next group, 3 drinks. How many people were in that group? 4. 4 times 3 is, you're almost there. It's a little bit more than 56. This one's 12, unless I did my math wrong. This one is 4 times 3. This is another 12. Okay, the next one is 10. And then there's a 1. So let's see, what do we have? 17, 29, 39, 41. Oh, wait a second. Did I miss one? Wait a second. I have a 57, so let me just check and see. 3, 2 times 7 is 14. 3 times 4 is 12. 12, 24. Oh, this is a 10. That's why it's off. Okay. Let's try it again. 3 and 4 is 17. 29. 39. 41. 51. Now I get 52. Hold on a second. I had 56 in my notes. Let's try again. This is 0. 3. 2 times 7 is 14. Times 4 is 12 and 12. 5. 2 is 10. Okay, you did get 57. So how come I'm coming up with that right now? Let me see. This is 3, right? 17, 29, 39, 41. I'm only getting 52. I have 57 down, but I'm not seeing. I don't know why. I'll have to go back and review this one. You're right. Thank you. There's my mistake. You're right. There it is. This is a 6. She got it. My mistake. Sorry. One person in here, but they bought 6 drinks. You're right. That's where it is. It should be 57. Thank you, Jacinia. I was going crazy because I knew I had the right answer. All right. Okay. Here's another one. Okay, here's one with TV sets. So they asked people, how many TV sets do you have in your house? How many homes are included in the survey? So how many people answered the question? Okay, the way you're going to get that is from the height of the bars. Okay, so what do we have? 2 plus 4 is 6, and 8 is 14, 20, 24, 27. I think I have 28. This one's 28 homes. So if I add the total, the height of the bars together, I should come up with 28. How many houses had 4 TVs? Who wants to try that one? How many of the houses in the survey had 4 TVs? 4. Yeah, it's 4, right. What's the modal class? Which is the most frequent of the answers? What did the families most commonly say? How many TVs did they have? 2. Yep. All right, and then this is just like the other question. How many total TVs were observed? Total TVs. So 0 here. Let's hope we can get this right this time. So there's a 4 here. Oops. This is a 4. And then 2 times 8 gives me 16. Tell me if I'm making a mistake here. 3 times 6 gives me 18. 4 times 4 gives me 16. 3 times 5 gives me 15. And then let's not make a mistake on this last one. It's a 6. So anybody add them up? It is 75, yes. 75 total TVs were observed in the survey or were included in the survey. Okay. A couple more displays to look at. The next one is called a frequency polygon. It's a line graph with scales. It's similar to the histogram. Let me show you one. It's easier to see what it looks like. So this is the pets one that we did before. So instead of having bars here, what they do is they start at 0, and then in the middle of the bar, at the height of the frequency, they put a dot. Okay, and then they connect the dots like that. It's called a frequency polygon. I don't know how commonly it's used, but your book has some samples in there, so I figured I'd include it. And you can read off it just like we did. So look at this one. This is the visits of families to the zoo. So look at this frequency polygon. How many families visited the zoo 4 times? 4 times. Go up here. How many families visited 4 times? Looks like, anybody want to try? 8. Yeah, it's 8. How many, okay, now here's where we get into wording. How many families visited at least 6 times? So here's 6. At least means 6 or more. So you're going to go this number plus this, plus this, plus this, plus this. Anybody get that one? 8? It's actually 24. I thought somebody had an answer up. It's not. 24. Whoops. Not at the bottom. Okay, so let me show you how at least 6 times. So here's 6 here. So this is 11 plus 9, 20, 23, 24. How many families were surveyed? So again, you're going to have to look here. How many families were surveyed? Add them all up. So you know this is 24, right? So all you have to do is add the remaining numbers. So 24 plus 5 is 29. That's not 5. 24 plus, this is 6. 30, 38, 46, 50. Looks like 52, I think. I got 52. 52. Yep, got some there. Okay, good. All right. Okay. Okay, here's another frequency polygon. How many people sent 6 or fewer text messages? Who wants to try that one? 6 or fewer. 6 or fewer. 16, yes. How many people are included in the display? Okay, so again, you've got 16 here, so all you have to do is go ahead and add up the remaining numbers, right? 36, yes, 36 is right. How many people sent 9 or more text messages? 9 or more. What do we have there? 6 plus 3 is, looks like 9. Okay, so these are pretty straightforward to read off of. Okay, another display your book talks about is stem and leaf. A stem and show you. There's stems and leaves. Let me show you. It's actually easier to look at one. So here's what a stem and leaf looks like. Here's the stem and here's the leaves. So the stem tells you, in this case, it's the tenths position in the number, and then this is the single digits. And so let's look at this data set here. They want you to construct a stem and leaf. The one thing to notice, this stem and leaf here is telling us there's data values of 21, 23, 25, 26, and 26. Are there two 26s here? Let's see. There's one here and there's one here. So this is the correct display right here. First thing I did was put them in order. It's a lot easier to see it that way. 21, 23, 25, and notice again, two 26s. The one on the left of right here only has 1 6. You have to have a leaf for every data value. So there's two 26s. If you look down here, there must be two 59s. There are, and there's two 61s. So this is the correct display. It's called a stem and a leaf. Okay, it's a really nice display. It looks kind of like a histogram, but it's a really nice display of data because you can get back to the original data values. Okay, I didn't know if somebody had a question. Okay. Circle graphs are also called pie charts. You've probably already seen those. Bar graphs. Bars don't touch here. Pie charts are helpful to compare the parts to the whole. So here's a pie chart. Here they're looking at the cost to attend a public university. Here's the total. And then the circle graph shows us the percent of the cost for the different categories. So 31.2% is for tuition, 39.5% is for the room, et cetera, et cetera. So that's what we call a pie chart or a pie circle chart, circle graph. The cost of tuition and fees is, so to get to the tuition and fees, what do? We take 31.2% of the total cost. Okay, and when you multiply that out, you get about a little bit less than $4,700. Okay, good, very good. Okay, and then, and watch if you're doing these in My Math Lab, how many decimals. The cost of the room is, so we're going to take 39.5% of the 14,000, and anybody want to do that one? 59.12, yep, round it off. And cost of the board is 22.8, so you're just going to multiply these. Right, good. And then lastly, the computer costs. Okay, the nice thing on a problem like this is you can add these up together and make sure you come out with a total tuition. So that's kind of a nice thing on a problem like that. It gives you a nice check. Okay, and they do add up. Okay, so that was your graphical displays. Really, all you need to be able to do is read them and interpret them. You're not going to make displays. So it's being able to interpret, read the frequency polygon, read the histogram, read the bar graph. I didn't do a bar graph here, but a pie chart, similar, just like this. Okay, so 13.4 is measures of central tendency. So if we have a data set, how can we describe it with a single number? And the first thing we might use is called the mean, which is also written like this, x bar. We add up all the data values and divide by the number of data values. Everybody probably knows that. It's also sometimes called the average. The mode we talked about before, the most frequent. And then we also have a mid-range, which is the value halfway between the lowest and the highest. So to calculate that, you add low plus high over 2. And then the median is the middle. If there's an odd number of data values, the median is the middle. If there's an even number of data values, the median is the average of the middle two. Okay, so let's try a problem. We're going to do all the measures on this one here. So first one I'm going to do is the mean. So what do? Add them all up, divide by the number of data values, and on this one it comes out to be 14. Okay? And then how about the median? Okay, they're nicely in order. They have to be in order, ascending order, for you to do the median. So there's 9 data values. So the median is going to be right in the middle. 1, 2, 3, 4, 5, right there. 13, yes, right in the middle. There's the median. If there was another data value here, if there was 10 of them, then you would average the middle two. But because there's an odd number, there is one number right in the middle. And then what's the mode? What's the most common data value in this data set? Okay, it's also 13 this time, right? And then what's the mid-range? Okay, mid-range is lowest plus highest over 2. And in this case, that comes out to be 17. Okay, so I'm going to just put them all up here on one screen. It's kind of nice to look at them all together. Generally, they're not going to come out to be the same number, and depending on the situation, you may want to pick one to report over another. So the mean was 14, the median was 13, 13, mode was 13, and the mid-range was 17. Okay? Now let's do a little application problem. The mean on a set of 18 tests is 82. What was the sum of all the test scores? Okay, so here's what we know. This formula, and they told us that the mean was 82, that's x bar, and they told us n. So we can put that into the formula, and they want us to find this. So what am I going to do? I'm going to multiply both sides by 18, and the sum is 1,476. Okay, so if you went back now and took this and divided by 18, you better get back to the mean of 82 that you were given. So just a little bit different way to think about the problem. All right, now the reason we did this one is because, let's work on a couple other problems along the same lines. This is the kind of question that instructors get a lot of times. So to get a B in a class, Alex has to get 80 on 5 tests. The scores on the first 4 tests were given here. What's the lowest score he can get on the last test and still earn a B? All right, so what do we know? We know this. We know that what he has to get an 80, so we know this has to be 80. There's going to be 5 tests, and we know all of his test scores except 1. So I'm going to let that missing test score be X. And all I did was take the formula for the mean, put in what I know, and this right here, change my colors, this is what I want to solve for. So what am I going to do first? Anybody want me to tell me what to do first to try to solve for X? What's the first thing I want to do? Yeah, you can add. That's correct. That's correct. Add, and then also, I did it in one step actually. I added them, and then I also multiplied both sides by 5. So this is 317, and then when I multiply by 5 on both sides, I get 400. And then I'm going to subtract the 317. And so Alex needs to get an 83 on the last test in order to end up with a B average. Okay, everybody with me? All right, let's do another one. Okay, good. All right, so to get a grade of B, the student has to have an average of 80. Jim has a mean of 79 so far, but he was on 10 tests. He comes to the teacher and he asks for a B, reasoning that he only missed a B by 1 point. What's wrong with Jim's reasoning? Is he really missing a B by 1 point? All right, so let's think about what we learned. The formula for the mean, here it is. And what does Jim actually have? He has an average of 10 tests, right? Is a 79. So is he really missing it? He earned 790 points. What does he need to earn to get a B? He needs to have that, which means he needs to have 800 points. So he really missed a B by 10 points, not by 1 point. His average is 1 point below it, but that's based on 10 tests. So this is not really, he didn't miss a B by 1 point. He actually missed it by 10 points. And that's the power of when you work with averages. All right, and then one other one here. The Taylors recorded their weekly grocery expenses for the past 12 weeks and determined that the mean weekly expense was $85.20. Later, Mrs. Taylor discovered that 1 week's expense of $74 was transposed and recorded as $47. What's the correct mean expenses for those 12 weeks? So here's what we know. We know the mean. We know there were 12 weeks, and that's how we calculate the mean. We don't actually know the sum, but that's okay. And we figured out, actually. So the sum that she used to calculate the average was this. But she made a mistake, didn't she? So she put down the 74 as a 47, so she actually added by $27. So if you add that back in, the true expenses are $87.45 per week rather than $85.20, because she put down a 47 instead of a 74. So another way to work with the mean formula. Sometimes we can make adjustments if we discover that something was wrong. Okay, so we did mean, median, mode, and mid-range, 4 measures of the center of a distribution, or the most typical, sometimes we call it. All right, so let's go on to measures of dispersion. So this tells us how spread out the data are. So are the data values tightly clustered, or is there a large variation among the data values? So the easiest one to calculate is the range, the highest minus the lowest. Also can do the standard deviation, which is the one that's a lot of calculations. So you're going to calculate the mean first, then you're going to measure the distance each data value is from the mean, square it, add those all up, divide the sum by n minus 1, and the last thing you do is take the square root. So let's work a problem. Okay, let's find the range and the standard deviation for this little data set here. All right, let's do the range first. The first thing you need to do is put them in order, okay, because the range is not just the first number or the last number minus the first number. They're not in order. So we put them in order. And so the range here is 17 minus 6, or 11. Okay, that was pretty easy. Now, to do the standard deviation, I do need the mean. So I added them all up, and I divided by 5, and I got a mean of 11. And let me see, I have a little table here. So here's my table. I took each data value and subtracted the mean. So 6 minus 11 gives me negative 5. Oh, there should be a 9. The calculation's right, but the number's wrong. There should be a 9 here. 9 minus 11 is minus 2. 11 minus 11 is 0. 12 minus 11 is 1. And 17 minus 11 is 6. Okay. Then I square those. We call these the deviations. I square those. So negative 5 squared is 25. Negative 2 squared is 4. 0 squared is 0. 1 squared is 1. And 6 squared is 36. All right. And then what do, add these all up. Okay, so when I added this up, I got 66. And then I take 66. Okay, hold on, Ernestine. 66, the sum of those, divide by n minus 1. There were 5 data values. 5 minus 1 is 4. 4 into 66 gives me 16.5. And then I take the square root, and it's a little bit greater than 4. Okay, Ernestine, what is it that you don't get? You don't get the table here? Okay. All right, let's go back to the prior screen. Oops, it's on the prior screen, actually. Here's the formula for the standard deviation. Remember order of operations. You go inside here. This means sum. This is called a summation symbol. You're going to take each data value, subtract the mean, we call that the deviation from the mean for the data value, square it, do it for all the data values, then add those square numbers up, divide by n minus 1, and then take the square root. So let me go back over to this slide. Okay, so here was my table. So here's the 5 data values, 6, 9, 11, 12, and 17. I take each data value and subtract the mean. I calculate the mean right here. So 6 minus the mean of 11 gives me negative 5. 9 minus the mean of 11 gives me negative 2. 11 minus the mean of 11 gives me 0. 12 minus the mean of 11 gives me 1. And 17 minus 11, the mean of 11 gives me 6. Then I square each of these. These are called the deviations. Then I square this number each time. So negative 5 squared is 25. Negative 2 squared is 4. 0 squared is 0. 1 squared is 1. And 6 squared is 36. Now I add those numbers up. 25 plus 4 is 29. 30 plus 36 gives me 66. Then put that into the formula. So this is the sum of the squared deviations is 66. Divided by n minus 1. 5 minus 1 is 4. 16.5 when I divide, and then I take the square root. So the standard deviation for this little data set is 4.06. Okay, using the same data set, let's just think for a minute. What if I added 10 to every number in this data set? How would that affect the mean? If I add 10 to every number in that data set, what do you think is going to happen to the mean? Remember, the original mean was 11. What happens if I add 10 to every number? How's the mean going to change? If you're not sure, you could calculate the mean over here. But actually, it increases, and it increases by that amount. It increases by 10 because I added 10 to every number. What would happen to the median? We didn't calculate the median on this one. The median is actually 11. It's the same as the mean. It's also going to increase by 10. How about the range? If you remember before, the range was also 11. Okay, the range doesn't change, nor does the standard deviation. Okay, and if you want to, after the chat, you can check it yourself. But interestingly enough, if you shift this, what we call a shift in a sample or a distribution, if you shift by a number, it changes the measure of center because you added or subtracted, but it doesn't affect the variation because all you're doing is shifting the whole thing up. So it's kind of interesting to think about when you make changes to data, what effect does it have on the measures of center and variation? Okay, so let's talk about, so that was 13.5. That's all we did in there was range, standard deviation. All we did. Okay. Now let's go to the normal distribution. And this section starts out with looking at histograms and their shape. So when we do a histogram, a couple shapes can happen. This is called rectangular or uniform. So across all the values that we're looking at, the frequencies are the same. This is what we call a uniform distribution. We could see a shape like this called J-shaped. So just different shapes we can see in the histogram. We can see 2 peaks. Remember what modal means is the most frequent. We could have 2 peaks called bimodal. We could have what's called a skew, where one tail in the histogram is longer than the other. Okay, and here's that skew again. The interesting thing about a skew is it pulls the mean towards the skew. So if you have a skew to the right here, it's going to pull that mean above the median. If you have a skew to the left, it's going to pull the median lower. The mean lower. Okay, that's what skewness does. It pulls the mean. And the most important distribution that we're going to learn about in this chapter, in this section, is the normal distribution. It's unimodal, 1 peak. If I folded it down the middle and put the 2 sides on top of each other, they're symmetric. Okay, normal curve. It's bell-shaped. Think about a bell. Symmetric about the mean. In the normal distribution, the mean, the median, and the mode are all in the middle, right here. Okay, another thing interesting about the normal distribution is called the Empirical Rule. And it tells us that about 68% of all the data are going to lie within 1 standard deviation of the mean on both sides. 95% within 2 standard deviations in both directions. and 99.7% within 3 standard deviations of the mean. This is called the empirical rule. It helps us to describe a data set. Z-scores. Okay, Z-scores are called standardized scores, and they tell us how far, in terms of standard deviations, a data value is from the mean of the distribution. And the formula is just data value minus the mean divided by the standard deviation. We call that the Z-score. Okay, and that empirical rule we just talked about kind of helps you gauge whether things are unusual. If you get a Z-score more than 2 standard deviations from the mean, it's unusual because 95% of the data falls within 2 standard deviations. So if your Z-score is bigger than 2, your data value is pretty unusual. Okay, so let's do some problems now. I have the normal table up here. Your calculator may do these for you, but I'm going to use the table. So it says find the area to the left of z equal 1.62. Okay, and I've got the table right here. And this is the table from your book. And I'll make it bigger. The first part of the table does the areas to the left, which is all negative z-scores. And the second part of the table, hopefully I got the whole table here. Yeah, I did. Gives you the positives, and we want it 1.6 to 1.6. I go right over here, and the area, and this is showing the area to the left, so I can read that one right off of the table. Just to summarize for you, on the normal table, area, all the area under the curve is equal to 1. So if I were to take all that area and add it up, it's a calculus problem, but it comes out to be 1. So let's go back here, and I actually put a picture here from the table. And that's what we just looked up. So I went down to 1.6, and then I went over to the column for the 0.02. So the area to the left of 1.62 is 0.9474. Okay? What's the area to the right? Okay. This is the z-score. This is the whole normal curve. So this is talking about a data value that's 1.62 standard deviations above the mean. And we want to know this whole area to the left. One thing to know, it's totally symmetric. So up to the mean here is 50%, and we're more than that. So what's the total area to the left? The table tells you that area to the left. So I went to the table. Here's the table. This is the same one that they use in my math lab. And I went down on the second part of the table for the positive z-score. So I went down to 1.62. So the area to the left of a z-score of 1.62 is 0.9475. So about 95% of the data lies less than a z-score of 1.62. Whoops, wrong one. Okay, let's do another one. What's the area to the right? The whole area is 1, so to get the area to the right, we just subtract it from 1. Yes. Let's do another one. Let's find the area between 2 standard deviations. Okay, what you're going to do on this one is you're going to find each area, the first area, the second area, and then subtract it to get the area in between. So let's look up 1.60 in that table. So when I go down to 1.60, here's the number here, 9452. All right, and then I'm going to look up 1.10, and I'll go show you that on the table. 1.10 is 8643 right there. And then I subtract. So the area between is 9452, the bigger number, minus the smaller number. So about 8% of the area is between those 2 z-scores. All right, let's do an application problem. A vending machine is designed to dispense a mean of 7.4 ounces of coffee into an 8-ounce cup. If the standard deviation of the amount of coffee dispensed is 0.4 ounces and the amount is normally distributed, find the percent of times the machine will dispense from 7.2 to 7.7 ounces. So the first thing you need to do is you need to get z-scores to work this problem. So let's get the z-score for 7.7. So I take 7.7, I subtract the mean, divide by the standard deviation. 0.75. A lot of times you'll see them written down like the z, and then the subscript is the number you're finding the z-score for. And then I'm going to find the z-score for 7.2. 7.2 minus 7.4, divide by 0.4. Notice this is negative because it's below the mean. Negative 0.05. I'm going to go to my table, and find those two areas. Oh, what happened? Hold on a second. Oh, okay, it's on the next slide. I'm sorry. I went too quickly. It's the same problem, it's just a little smaller here. So we found this, have this z-score, so we want to find the area to the left of 0.75. So in the table, I went down to the row of 0.7, and I go over to 0.05. So there's the area to the left. All right, and then I'm going to look at negative 0.5. This is on the first part of the table. Go down to negative 0.50, 3085, and I subtract. So about 46.49% of the cups dispensed are going to have between 7.2 and 7.7 ounces of coffee. Okay. Everybody still with me? Okay, let's do another one. Okay. Assume the annual daycare cost per child is normally distributed with a mean of $6,000 and a standard deviation of $1,500. In a random sample of 150 families, how many pay more than $45.75 annually for child care per child? All right, we need a z-score, and we need it for this number here. So $45.75 minus $6,000, the mean, divided by the standard deviation, gives us a z-score of negative 0.95. I'm going to go to my table. Now notice we're working with the area here. So what do? We find this area and subtract from 1. Okay, because the table gives us the area to the left. We actually want people who are paying more. We want the area to the right. So I go to my table, negative 0.95 right here. Okay, subtracted from 1. So about almost 83% of families are paying on average more than $45.75 for daycare. Draw yourself a picture so you can orient yourself. That's why I showed you that little picture back here. Make yourself a picture so you have an idea of where you are in the distribution and which area you want to find. If you want the area to the left, less than, you read it off the table. If you want the area to the right, you'll find the area to the left, and then, just like I did over here, then subtract it from 1, which is what we just did here. So about 82.89% of families pay more than $45.75. We know it's more than 50% because this number of $45.75 is below the mean. So we know it's going to be more than 50%. So that kind of makes sense to us when we think about it. Now, there were 150 families, so if this is the percent, we want to know how many families. We take 82.89% of 150, and we come out with 124 families. So out of 150, we would expect 124 to be paying more than $45.75. Okay. All right, let's try another one. The warranty on a car battery is 36 months. If breakdown times of this battery are normally distributed with a mean of 46 months and a standard deviation of 8 months, determine the percent of batteries that can be expected to require repair or replacement under the warranty. Okay, so here's our mean and here's our standard deviation, and we want to know what percent of them are going to last less than 36 months. Okay, so we're going to find a z-score for 36 months. So 36 minus 46 over 8, the standard deviation gives us negative 1.25. Okay, so I'm going to go to my table, go down on the first part of it, negative 1.25. So we expect about 10.5% of batteries are going to be needing repair or replacement under the warranty, assuming the mean life is 46 months with a standard deviation of 8 months. Okay. All right. Let me see. I'm trying to see. I have a lot of problems here, so I think I might skip over some of these. Let's see. All right, well, let's see if we can get through them. We've got 10 more minutes. So, horseback rides. Assume the length of time for a horseback ride at this ranch is normally distributed with a mean of 3.2 hours and a standard deviation of 0.4. What percent of rides will last at least 3.2 hours? Now, notice the mean is 3.2. So what percent of, remember the normal distribution? Let me get my pen here. Remember the normal distribution. I'm not so good at freehand sketching here, but if the mean was right in here, what did we say? What percent of the data were going to be greater than the mean and what percent were going to be less? Remember, it was totally symmetric, so what do we expect? 50%, yeah. So you don't have to do any calculations on this one. You expect 50% of rides to last more than the mean, just by the symmetry of the distribution. What percent of the rides will last less than 2.8 hours? So we need the z-score for 2.8. 2.8 minus the mean, divided by the standard deviation, so I get a z-score of -1. And if I go to my table, and if you go to the table, let's go back, go up to the negative part, -1.0 is here, 0.1587. So we expect about 15.87% of the rides to last less than 2.8 hours. What percent of the rides are at least 3.7 hours? So we need a z-score for 3.7. 3.7 minus 3.2 divided by 0.4 gives me 1.25. And let's go over to our table. So 1.2, so you can see it, 1.25, 89.44. Okay, but this is the area to the left. We really want the area to the right. So what are we going to do? We're going to subtract it from 1. It should actually say 100%, but about 10.56% of the rides are going to last at least 3.7 hours. What percent of rides are going to last between 2.4 and 4 hours? Again, we need the z-scores for 4. And the area here to the left of this is 97.22. And then the z-score for 2.8. Oh, I didn't put the z-score up for you. Oh, we already did this one. That's why. It was done in an earlier part of the problem. We got 15.87. So we subtract. So we expect about 81.85% of the rides to last between 2.8 and 4 hours. There was the one we just did pictorially. So you find the larger area, the more positive z-score, the smaller z-score, and then subtract to find the area in between. In a random sample of 500 horseback rides at this ranch, how many were at least 3.7 hours? All right, and we did this in Part C. We found the answer for this was 10.56 in Part C. And so if we have 500 rides, all we do is find 10.56% of 500. So it's about 53 horseback rides would last at least 3.7 hours. All right, and last scenario. Assume the waiting times for customers at a popular restaurant before being seated are normally distributed with a mean of 12 minutes and a standard deviation of 3 minutes. Find the percent of people who wait at least 12 minutes before being seated. Notice again, the 12 minutes is the mean, so this answer, without any calculations, is just 50%. Find the percent of customers, and here's a shorthand way we frequently write normal. Normal distribution, mean, standard deviation. Find the percent of customers who wait between 9 and 18 minutes before being seated. So just like we did before, we need a z-score for 9. 9 minus 12, so we get a -1. And we need a z-score for 18, which is a 2. We look them up on the table. For a z-score of -1, it's 0.1587. For a z-score of 2, it's 9.772. This is real similar to the one we just did for the horseback rides. So about 81.85% of the customers are going to wait between 9 and 18 minutes. Find the percent of customers who wait at least 17 minutes before being seated. So same step again. You need a z-score for 17, 1.67. And if you look that up in the table, 1.67, I'm on the positive one, yeah, 1.6, oops, got to go across, 1.67 is 9, 525. That's the less than, but we want greater than, so what am I going to do? Subtract it from 1. So 1 minus, about 4.8% of the customers are going to wait more than 17 minutes. And find the percent of customers who wait less than 8 minutes. Find the z-score. And you're going to look up in the table for z equal negative 1.33. The area to the left is 0.0918. So about 9.2% of the customers wait less than 8 minutes. I think I have one more. Oh, okay. Here's just a wrap-up problem. Assume the number of hours college students spend working per week is normally distributed with a mean of 18 hours and a standard deviation of 4 hours. Determine the percent of college students who work between 14 and 26 hours per week. Show your z-scores and the area between. So what's the z-score for 14? So what are we going to do? 14 minus 18 divided by 4 gives us negative 1. So that's going to go here. And the area to the left there, if you look it up on the table, is 1587. And then we're going to do 26. Z-score is 2. And the area to the left is 9772. And the area between is 8185. This is the same numbers we had before. So we expect about 81.85% of the students to work between 14 and 26 hours per week. If you notice, some of the z-scores come up a lot over and over again. Negative 1, positive 2. They're common ones that you'll see used frequently in the problems. All right. So that's the end of the material for chapter 13. So any questions as we're finishing up? The material is not difficult. You just have to learn to use the table for the normal distribution. Standard deviation, make that little table for yourself. Or your calculator may already do it for you too, if you have a TI-83. But you can do the standard deviation on a paper and pencil if you use that little table. All right, so any questions as we finish up? No? Good. Okay. Yes, take a look at the final exam prep quiz and you'll see all the formulas that are going to be available to you. Because there's a lot of formulas from chapter 9. So, yes, the table will be there, yes. For this chapter, you'll get the z-score formula and the table, like I just showed you. That same table will be available. And if you take the prep quiz, you'll see it. When is the test, Ernestine? The test starts on July 17th, 18th, and 19th. I know you take it in the testing center, so you're going to need to make an appointment. I'll email you separately about that. But the proctored tests are given on July 17th, 18th, and 19th. And this is the last set of material that's on the final. Okay, well, if everybody's good, I'm going to go ahead and sign off. Yes, Ernestine, in the Unit FE Final Exam module, there is a preparation quiz. You need to submit the student survey of instruction to unlock it. But look in the Unit FE Final Exam module in My Courses, and the student survey of instruction is there. Once you've completed that for me, which gives feedback about how the course was, then you'll have the access to the prep quiz, just like you had for the midterm, okay? All right, well, I'm going to go ahead and sign off, everybody, so have a good evening. And you can email me if you have questions as you're working on your problems, on your homework. Okay, so have a good night, and we'll chat again next week. We'll have a final exam review chat. Okay, good night, everybody.